Alright, so today I'm going to be explaining this important paper with the title Diffusion-free Graph Generation with Next Scale Prediction. This ICML paper in 2025. Autoregressive models excel in efficiency and plug directly into transformer ecosystem, delivering robust generalization, predictable scalability, and seamless workflows such as fine-tuning and parallelized training. However, they require an explicit sequence order, which contradicts the unordered nature of graphs. In contrast, diffusion models maintain permutation invariance and enable one-shot generation but require up to thousands of denoising steps and additional features for expressivity, leading to high computational costs. Inspired by recent breakthroughs in image generation, especially the success of visual autoregressive methods, we propose MAG, a novel diffusion-free graph generation framework based on next-scale prediction. By leveraging a hierarchy of latent representations, the model progressively generates scales of entire graph without the need for explicit node ordering. So there are three main issues of autoregressive graph generation. First is long-range dependency. Generating nodes one at a time results in sequential dependencies that make it difficult to capture long-range interactions and global structures. The second one is forced node ordering. Enforcing a specific node or ordering is at odds with the inherent invariance property of graphs, forcing the model to learn over a specific ordering, thereby increasing complexity and reducing generalization. And finally, inefficiency. Generating a graph sequence with a conventional self-attention transformer incurs order of n autoregressive steps and order of n cubic computational costs. Drawing inspiration from image generation, for example, visual autoregressive modeling, our approach suggests a new ordering for graphs that is multi-scale coarse to fine. We introduce MAG, a novel transformer-based graph generation based on next scale prediction instead of traditional next node and next edge approaches, thereby infusing autoregressive properties with graph structural constraints. And this is the overview of the multi-scale graph generation framework. The input graph is first encoded through a message passing neural network. So here it is encoded, which produces a latent representation that is quantized at multiple scales. A transformer then predicts the scales autoregressively via coarse to fine next scale process. And finally, a GCN is our decoder to reconstruct the graph from discrete latent representation R sub k. So these are latent representation, R1, R2, R3, Rk, that we give it to the transformer. Because they are quantized at multiple scales. There are also other ideas that in the autoregressive diffusion, like PARD, this paper from Carnegie Mellon, that first partitions the graph into blocks, applies diffusion within each block, and autoregressive between them. And it introduces partial ordering, which enforces permutation invariance. but its block-wise diffusion introduces extra implementation complexity and it still incurs substantial sampling costs. But GraphArm, this one instead embeds diffusion steps into an AR framework, autoregressive. At each forward pass, a single node and its edges stochastically decay, making the model both permutation and order sensitive. Beyond these hybrids, pure coarse-to-fine strategies have also been explored in this reference that grow a full graph from one seed node using localized denoising diffusion. So all of these rely on either block-level diffusion, node-level decay process, or strong domain priors such as motif libraries. But our framework is different. So you see, this is the general autoregressive model in graph. And then they use this quantizer. A quantizer is used to convert each scale's latent representation into discrete tokens. The quantizer includes a codebook containing weak learnable embeddings for which each feature's dimension is maintained by convention. So during quantization, Q is obtained by replacing each feature vector from the multi-scale latent features F by its nearest code Q. So this one selects the width vector in codebook Z, the one that minimizes this distance. So it is trained by fetching all Q and minimizing the distance between Q and F. And then we use a decoder to reconstruct the original graph from its final discrete latent representation. So your decoder is just a GCN. So we have level embedding and scale sampling. A level embedding is learned to encode the scale at which a token operates within the input structure. Scale sampling during training and inference, we select scale sizes from a predefined set of length. So we fix the first scale to 1 and the final scale to n, and n is the target graph size. Intermediate scales are chosen from the predefined set. So these are the samples of generated generic and molecular graph of MAG. These two datasets are very important for graph generation of molecules. And this is the wall clock inference time that are in seconds for 50 and 100 samples. These are results on QM9 and zinc 250K molecule dataset. You see validity, uniqueness, novelty, FCD, as well as time.